Log on, tune in, find out. Another good idea from Cambridge.
But he still accepted to give a talk after doing how many hours of lecture, whatever?
Let's not count.
Okay, anyway, please, I don't know the title, so I just write it down.
Okay, thanks very much. Thanks for the invitation. Very happy to be visiting the Newton Institute. It's a completely different universe. Okay, so I'm aware that I'm aware that most of you here are not probabilists, so I'll try to not speak about probability, or at least give a lot of explanations. So also one thing that I'm very pleased about is that I know that there was a first Barry Sticky was mentioned earlier during the day, and you have a second one talking, and it's joint work with a third one. So in fact it's joint with so my brother Julien, and Jason Schweinsberg. So he's in San Diego and Julien is in Paris 6. So the topic of the talk is about the effect of selection on the genealogy of population. And in order to explain this, to explain a bit what's the status of the problem, I'll start with something very basic, which is the case of population, fixed size population with no selection at all, and I'll try to say what do we know about these populations. Okay, so it all starts with a very basic and simple model, which is called the Moran model. And so what this is? This is a certain population which evolves randomly, and what we care about is in this population is really how do lineages look like? What can I say about the ancestral lineages if I sample from this population at a given time? Okay. So you assume that you have a fixed size capital N. So these are my N individuals. So I'm going to label them like that. So here's individual 1, individual 2, etc. And each individual lives for a certain amount of time, which will be a random variable for everyone. It will be an exponential random variable. And when they die, I'm going to declare that they get replaced by somebody else, which will be the child of some randomly chosen individual in the population. Okay, so they all live for a while, and maybe individual 2 dies after a certain amount of time, okay, which is a certain random variable which I take to be exponentially distributed. It doesn't matter. So at this time it dies, and what happens is that it gets replaced by somebody else, which is the child of an individual which I choose randomly in the population at this time. Okay, so maybe I pick this person to be the father. Okay, so this is instantaneous. Maybe I should do it like that. Maybe individual N makes a child at this instant, and this child occupies the position number 2 in the population. Is that clear? What this looks like, this thing? So individual keep going, and it's the same thing all over. Now maybe this person dies, and he gets replaced by let's say by a child of individual number 2. Okay, at this instance. Is that clear? How this evolves, this population? Okay, so I make change. Everybody lives for an exponential amount of time. It's a random variable. It's the same distribution for everyone. When it dies, it's replaced by a child of some randomly chosen individual. So what do we care? So as I said, what we care for, what we're interested in describing is the genealogical relationships between individuals sampled in the population at a given time. Okay, so let's say we fix time t and sample, say, k individuals in population at time t. Okay, so what are the genealogical relationships between these individuals?
Excuse me.
Yes.
When you said that individual n, for example, replace the individual 2,
Yeah.
what happened to the original individual 2 then?
So two is dead now.
Right?
Okay.
Then what?
And it's so there's a new individual here. It's a new individual 2,
I mean,
and he's a child of capital N.
What happened then to the individual n?
Well, N is still alive, and he's made a child. He's made a new child. So there's, if you think that these people are carrying allelic types, then the allelic type.
So the reproduction of individual n will correspond to
Right.
death.
Exactly. So that's another way to think of it,
Right.
is that every person in this population reproduces at rate 1, and when it reproduces, it puts its child on the position of somebody in the population which dies.
All right.
Okay? So that's another way of thinking about it, but yes, it's exactly the same system. Okay, so here's the, I mean, there's every individual plays the same role. There's no space, there's no difference between individuals, there's no selection, no nothing. Okay? It's really perhaps the simplest model of population that one can think of. So I'm interested in describing the genealogical relationships between individuals in the sample, in the population. So maybe I'm sampling, you know, this one and this one and this one. And you know, so what do you mean by genealogical relationships? I mean, really, you know, what's the time to the most common recent ancestor between all individuals in my sample, or what's the time of the most recent common ancestor between individuals 2 and 3 in my sample? Okay, something like that. So a very convenient way of studying this problem is through what's called the ancestral partition. Okay, so the ancestral partition is something that tells me, okay, so this is time capital T here, and I can look at time t minus t and ask, well, who among the individuals in my sample share a common ancestor at this time capital T minus t? Okay. So we introduce the ancestral partition. So this is something that I'm going to call pi t, and there's an n, and there's a k. So little t is varying between 0 and capital T, and this is defined as follows. So defined as follows. So once you sample k individuals from your population at time capital T, first of all, pi t and k is going to be a partition of 1 through k. So this represents the k individuals in your sample. And I'm going to put I and j in the same block if they share the same ancestor at time t minus t. Okay, so they are going to be in the same block if same ancestor. So this is exactly the right. So this is something that really keeps track of the genealogical relationships. It's a very convenient way of describing the genealogical relationships in a sample. Okay, so let's maybe it's good to do some sort of simulation. Maybe I'll take some colors. maybe let's have something something exciting, maybe like that. Okay, and maybe like that. Right. Okay, so we have 3, 4, 5, and 6. So these are, so I'm sampling k equals 3 individuals from the population at time capital T. Okay, so let me call them A, B, and C, say. So what's the status of my partition at time little t equals 0? So at time little t equals 0, I've sampled individuals that are different, and so nobody shares the same ancestor, and so the partition consists only of singletons. Okay, so we have pi 0 and k, so this is just the partition which contains only singletons. And then as I move little t in this direction, I see that eventually I have some lineages that may coalesce. Okay, so for instance, at this time here, I have that lineages corresponding to individuals C and B are coming together. C was a child of individual B here. Okay, and so at this particular time, so this is at time T1, we have that now. So maybe if I have to be consistent, let me call it A, B, C here. Okay, so A, B, and C. And at time T1, we have that pi T1 and K. Now we have that C and B have coalesced. So A is still in its own singleton, and B and C have coalesced because they now share the same common ancestor prior to that time. Okay, and then time still goes on, and we see that before B and C have a chance to coalesce with A is actually coming to this individual. So if this is what I know of the process, then nothing changed until later. Okay, so as I move along, nothing much happens in my simulation. Okay, so if this was time 0. Okay, is that clear how this evolves, this process backward in time? So eventually, I mean, in principle, I could also imagine that this, there's a stationary version of this where time can go as far as I want to the left, and then eventually, if I run this thing long enough, eventually all lineages would coalesce, and this will be the time where I found the most recent common ancestor in the sample of my population. Yep.
But in this situation, A, B, and C have coalesced at time 0 because you have this arrow from A to B, don't you?
No. Sorry, it's in the wrong direction. Yes, you're absolutely right. So, excuse me, I didn't read my simulation well enough, because indeed what happened at this instant was that individual 2 made a child and replaced individual 1. Okay, so the ancestor of this person is still here. Okay, so in fact you're right here. So this was T1, and now we have T minus T2. So in fact my simulation was more exciting than I thought. Excellent. So then, indeed, at T2 here we have that all these individuals share the same common ancestor, and so we have found the time to the most recent common ancestor. Okay, so this way of tracking the ancestral lineages of samples in the population is really a very convenient framework for looking at the genealogical relationships between in the sample. Okay, is that clear? In fact, a lot of the information that can be relevant in theoretical population genetics, things like what sort of diversity do we observe in the sample, what sort of genetic variation do we observe in the sample, can be reconstructed from just understanding the way this coalescent process evolves. Okay, so here's the question. can we describe this process in a simple and tractable way? Okay, and here the answer is yes, we can, because it's a very simple process, a very simple model, and the answer is a very nice and interesting Markov process called the Kingman's coalescent. And basically, to do that, what you have to do is you have to speed up time by a factor n minus 1 over 2. In fact, so if I speed up time by total population size minus 1 divided by 2, so this is the following process. So it's a process which evolves randomly and which evolves according to Markovian dynamics. So for those of you who don't know, Markovian just means that, you know, I don't care how I got there. The only thing that matters is what's the current state of my partition. And is Markovian, and so all I need to tell you in order to describe this process is what are the transition rates. And the transition rates are very simple. They are simply that every pair of ancestral lineages merges at constant rate 1. Okay, so I could have ignored the population dynamics underneath and just reconstruct this evolving partition, this coalescent process, by doing the following thing. Initially, I have k blocks. Okay, there are k ancestral lineages, and each pair of them is merging at rate 1, which means that for each pair, I throw an exponential random variable with rate 1, and I look at the clock. I look at the random variable which comes out to be the smallest. Okay, so I have k choose 2 clocks, and I look at the clock that comes first, and this is the clock that I choose to merge. So then I merge this pair of lineages, and now I have k minus 1 blocks, and I can keep going these dynamics. Okay, so each of the new pairs, each of the pairs of among k minus 1 ancestral lineages now is trying to merge at rate 1. Okay, and this keeps going, and eventually I end up with all individuals have coalesced together, and there is just one block in my partition. And to see that this really is a description of this process is a very simple game with Poisson processes. So it's not there's nothing very deep about it. It's quite simple. So this is what's called a Kingman's K-coalescent. And the interesting feature about Kingman's coalescent is that, although here I introduced it to describe the genealogical relationships in a sample from a very, very specific population dynamics, the Moore model, which is really extraordinarily simple, it turns out that this is the correct scaling, what's called the scaling limit in many population dynamics that share a number of features that are always the same. So what I'm trying to say here is that the Kingman's coalescent here, the rule that I've described to you here, this is the correct way of describing the genealogy of a sample in many, many populations. Okay? And for this, you need a number of features. You need, first of all, that there's no space. Okay, so completely well-mixed population. You need, so every individuals look and behave the same. You need no selection. Okay, so no individual plays a spatial role. So that's very important in this story here. And finally, you need that the typical number of offsprings of a given individual doesn't behave too badly. And this means, you know, you shouldn't have too many, you shouldn't be allowed to have too many offsprings. So if I think of the if I think of the offspring distribution of a randomly chosen individuals, this should have a finite variance. This is the technical condition. So I'm not going to go into that. What I want to do, is to explain what happens when in a simple system you really add selection. How different does it look like? Okay, so this is the big question. What can you say when there is selection? So you have to trust me a bit that Kingman's coalescence is really the rule, the universal, is a universal rule when there's no selection. Kingman is universal, with no selection. And one other thing that I want to say about it is that not only it's universal, it's universal for many models, but also the order of magnitude for the sample of individuals is always going to be of the order of the population size. Okay, so for instance, the time to the most recent common ancestor is always of order n. Okay, so by which I mean that if you divide by the population size, then this converges to a non-trivial random variable as capital N tends to infinity. So the question is, what happens when you add some selection dynamics? And to do this, recently there's been a very interesting model suggested, very simple, very interesting model suggested by physicists Brownian and Derrida. And this is the following model. So it's also fixed size. And so in this population model, every individual is represented by a point on the real line. And I think of the point on this real line as being the fitness of this individual. Okay, so we have a cloud of particles. On the real line, and so to tell you the evolution, there's a two-step procedure. First, individuals reproduce and branch, and then they're selected. Okay. So let's say this is what it looks like at time t. Okay. So we have here n equals 5. So this is my cloud of particles. So this is the respective fitness of individuals in the population. And to describe the population at time t plus 1, I'm first going to tell you what it looks like at time t plus a half. So at time t plus a half, what I do is I let everybody have a number of offspring, say 2 offsprings. And okay, so maybe, so what I'm trying to say is that in this model, what happens is that the fitness of the child is perturbed by some independent noise. So we imagine that, so this represents the effect of mutations, for instance. And we imagine that the fitness of the child is just the fitness of the parent plus some independent random variable, say Gaussian random variable. Okay, so you add to the position of this person a Gaussian random variable. And you do that for every child, for every person in this population. Okay? So what I've done is for each position here, I obtain this by adding to the father an independent normal random variable. Okay? So now I have 2n individuals in this population, so I have to do something to keep the population size fixed. And what I do is I simply cruelly kill the n worst and keep the n best individuals in this population. So 1, 2, 3, 4, 5. So this is the cutoff. and I keep that. So this is t plus 1. So I keep the n best. Okay. So we have 2, 3, 4, 5, 9. So here. Okay. So this is now my population at time t plus 1. Okay, and I keep going and doing this repeatedly. I can do that as long as I want for time infinity. And the question that you want to know about this cloud of particle is, first of all, what does it look like? Does it drift to the right? At what speed? Does it diverge? What are the genealogies of this population? What's the time scale even for the genealogies of this population? So they made some they had lots of arguments. None of them rigorous, but none of them crazy. In fact, they're really very nice and interesting arguments. And they made the following predictions. So first of all, the cloud of particles drift to the right with a certain limiting speed. Vn. And they gave a formula for Vn also. So Vn is, well, it's always V infinity. In the case of Gaussian, it's square root 2 minus some constant over log n squared plus little of 1 over log n squared. So when I say limiting velocity, I mean limiting in t. Okay, so if you look at the asymptotic velocity, asymptotic in t velocity of this cloud of particle, it's Vn, approximately Vn. And so that's the first prediction that they made. The second prediction that they made is that the correct time scale for the genealogy of the population, so things like the time to the most recent common ancestor in a sample of size 2, 3, 10, or whatever you want, is this funny exponent log n cube. So not only that, but they claim that if you measure time in units of log n cube generation, then when measuring time in these units, then there is a nice process in the limit which describes the evolution of the ancestral lineages. And this nice process is the following. So again, I have to think of this ancestral partition process. So fix k greater than 1, let t be strictly positive, sample k individuals from the population I times t log n cube. Okay, and form the ancestral partition process. So this is something that I can call pi n k t for t less or equal than t log n cube. And they claim that this has a limit as capital N tends to infinity. So if I measure time, if I speed up time by log n cube, so now little t is varying between 0 and capital T, then this converges in the sense of finite dimensional distribution, doesn't matter, towards an interesting limit, which depends only on k. And so this is capital N tends to infinity. And this limit here is this very interesting limit. It's called the Bolthausen-Sneedman coalescent. So I don't assume anyone in this room knows what it is about the Sneedman coalescence, so I'll give a description in a second. But this is, before I do that, let me just say, first of all, this is really quite remarkable. We have a completely different scaling for the, for the time for quantities like time to the most recent common ancestor, and everything else will be different as well because of this log n cube scaling. So before, without selection, we had a time to the most recent common ancestor of order n. Now it's a time of order log n cube. Okay, and before we had the genealogies described by this Kingman's coalescent. Now we have genealogies described by this Bottas and Sneedman coalescent. So let me describe what this is. Yeah.
Does this depend on the fact that the size of the number of the children of an individual is deterministic, or would this also apply if it's a well-behaved random variable?
Yeah, no, it doesn't depend very much on the offspring distribution. You could give them 10 or anything random. If you're allowed to have zero children, it's a bit more messy. You have to condition on non-extinction. But if you make it supercritical anyway, that's not a big issue. But so it doesn't depend on the offspring distribution. Doesn't really depend on the random variable that I choose for the perturbation. I took Gaussian here for the sake of definition, but if I change my random variable, then it would change some constant. I would have to run the Bottas and Sneedman coalescent at a different speed. Yeah.
It depends on your selection scheme, right? If you just reproduce with a probability that is proportional to your selective advantage, that would be different.
Sorry, it depends on what you say.
If you just reproduce with a probability.
Depends on the selection scheme.
Your selection scheme is highly unusual. This time-hitting selection.
Yeah, it's yeah. I mean,
it will be in general. It will be sensitive to that, right?
Well, to what extent is it sensitive to that is a very wide open question.
So how does it compare to Hudson's and Kaplan's result then?
I'm not sure I know enough about other models of selection to comment really on the.
In the coalescent process, okay.
But one thing that I can tell you is I mean, we know very little of. I mean, in principle, you can imagine all sorts of models in between the completely neutral case that I described before and this. So you don't select the n rightmost individuals, but you select them, with an advantage if they're further to the right or something like that.
Breeder does. Like a breeder may do the truncation selection, but in nature this is quite extreme. So if you
sure, it is very extreme. Yes,
in
no doubt.
situation, you probably want to select. You
No,
want to reproduce a probability.
No, you're entirely right. I mean, I think it's completely right to discuss the.
But it's nice that you get
to discuss
it's a limit, right?
Yeah, no, I completely agree. I mean, this is a very sort of naive and idealized and maybe unrealistic model, one might say. But nevertheless, I think it's interesting because it shows that adding some selection really completely changed, I mean, radically the way we expect things to look like. Okay. Okay, so I should perhaps describe to you what this Bottas and Sneedman coalescent looks like. And this is also a Markovian process. So it's also Markovian. It's also, a partition of 1 through k. And so again, I only have to tell you what are the transition rates. And so here it's very simple. If there are B blocks, then any m of them will coalesce at a certain rate. Any m of them coalesces at a rate which is called lambda bm, and which is given by a certain integral formula, which is p to the m, 1 minus p to the b minus m, and then there's p minus 2dp. It turns out that you can compute these integrals because it's just a beta integral. But so there is an expression which is more compact than this integral, but I like this one because you can understand a lot about this process when you just look at this integral. Okay, so in particular, so one way to read this integral is to think of the following thing. What happens is that at rate, okay, so this is the same thing as the following description. At rate p minus 2 dp, then you have the following event. So you have that every block tries to toss a coin, and the parameter of the coin is p, so it comes up head with probability p. Okay, and every block that comes up head, I decide to merge them together. Okay, so p minus 2 dp, this is a big rate when p is very small. So you have a lot very often in time. In fact, on a dense set of times, you have that you have this small coalescence event where a fraction p, which is very small, of all blocks decides to coalesce. Okay, and it's decided by this coin tossing procedure. And you have this takes a bit of work to make rigorous as a description because of this explosion when p is very small. So you have a lot of those events, but it actually makes sense, the description. And once I write it in this form, it's sort of obvious what this integral means. If you want m blocks to coalesce, then they all have to say yes to the coin tossing. So all m of them has to say yes to the coin tossing. All the other b minus m of them have to say no to this coin tossing. And this is the rate at which the parameter p occurs in this process. Okay? I hope this is more or less clear as a formula. So you see that one of the things that's remarkable about this Boltzmann coalescent is that in particular it allows for several blocks to merge at a given time. Okay, so you can have as many blocks merging together. Maybe all of them will merge. This is what you'll see in your sample. Maybe all of them will merge right away. This is possible. This is certainly very, very different from Kingman's coalescent, where you only have binary mergers occurring at any given time. You have only pairs of lineages coalescing together at any given time. Here you can have many more.
But it's similar to the lambda coalescent.
It's exactly, this is in fact a specific case of lambda coalescent, where lambda is just a uniform measure on 0, 1. Okay? And if you think about this model, this might seem very strange. Why do I have in the limit a process which allows for multiple mergers when in my model, at any given generation, any person has only 2 offsprings, so I can only have 2 pairs of lineages coalescing together at any given time. So what's happening is that really we're speeding up time by log n cube. So in fact, there are many of those pairwise mergers that happen very quickly together on the scale of log n cube. And so when you pass to the limit, they appear as if they happen all of them at the same time. So, in fact, this prediction came with an even more strong prediction of why these multiple mergers occur, and this has to do with the fact that, and in fact, this is a prediction. This is something that we can also make rigorous. I'll explain more what we can do about this model. And the idea is that what's creating those multiple mergers is that once in a while you get a lucky particle. That lucky particle makes it far away to the right. Okay, much further away to the right than the rest of the population. In fact, how far away? Exactly 3 log n away from the rest of the population. It doesn't matter. Once this lucky person makes it far away to the population, far away from the rest of the population, it's in a very good position. Okay, its offspring will reproduce and will not fail the selection for a very long time. Okay, and this is just enough. This threshold 3 log n away from the rest of the population is just enough that this guy has the possibility of generating very quickly a positive fraction of the entire population. And this is what leads to this positive fraction of lineages coalescing at any, instantaneously at any given time when you speed up time. Okay, so this is a prediction. I think it's a very nice model. Let me say that, as stated, this is really very much a prediction. We absolutely don't know any proof for this model whatsoever. I should say that the fact that the cloud particle drifts to the right with this velocity, this is known. This is now known rigorously. But for the genealogies, we don't know anything.
if the truncation point is changed, then you simply introduce another constant, or you just get a different C.
If you
select not 50% but 10% or 90% of the population.
but then you see, I mean,
Because then
I have to keep population size fixed. So here what I did is that I let everybody have 2 offspring, and then I select 50%.
But if the number of offspring is k,
Right, and I would select the first 1 over k percent. It would be exactly the same. I will speed up the Boltzmann correction, but it's the same object in the limit. Okay. So what I'll do is I'll now state a theorem, which this we can prove, which is motivated by this problem, but it's simpler in some way. It has some features in which it's different. And here's the idea. If you try to follow if you try to ignore selection for a second, and you follow the position of the offspring of certain individuals, you see that all the offspring are taking a random walk step away from this person. Okay, so in effect, what we're looking at is something that's very well known, and it's called branching random walks. Okay, so we have every particle is branching into 2, and the position of the offspring is just a random walk step away from the parent. Okay, so the first thing, of course, this is ignoring selection. We have this funny selection system. So what I'm going to do is essentially modify branching random walk for something which is simpler to study, which is branching Brownian motion. Random walks is discrete and so hard to study. Brownian motion is continuous and therefore easy to study. And then the second thing that I do is I'll change the selection rule, which is much too complicated for us. So consider the following system. So every particle, so initially there is one particle at some position that I'll say what it is later. Then every particle branches at rate 1. So instead of speaking of discrete generation, I'm going to have continuous time. So every particle branches at rate 1, moves according to Brownian motion on R. Okay, so for the moment there's no selection, but I'll do that in a second. And so if I have to make a movie of this, I have initially this one particle and it's moving like a Brownian motion. Then after some exponential amount of time, it divides in 2, and the 2 offspring are doing Brownian motion, etc., etc. Okay, then this one divides, etc., etc. Okay, so that's branching Brownian motion. In order to introduce a bit of selection, rather than keeping always the n rightmost individuals in this population, what I'm going to do is have a wall that's moving at a good speed, good enough that the number of individuals will be approximately n. Okay, I'm going to have a wall moving at a certain speed, and when the particle hits the wall, that's it, it's dead. Okay? Plus moving wall at speed mu. And when the particle hits the wall, it's removed. Okay? Removed is more politically correct than killed, I think. So I'll do that. Okay, so we have this selection wall, and if the particle just happens to, if selection happens to catch up with that particle, then it's killed. We kill it. We remove it. Okay? And the hope is that if I choose my selection speed good enough, well enough, then I have a system which reproduces essentially this fixed size population system that I'm looking at here on the right hand side. Okay? And indeed, this is true, but maybe, okay. Indeed, this is true, but it turns out you have to choose. You have to choose the speed of the wall appropriately. So here's, oops. So here's the theorem. So this is joint with the two authors that I mentioned at the beginning of the talk. It turns out that if you want to have of order n individuals, you have to make a very specific choice. The speed of the wall is approximately square root of 2 minus a correction, and this correction happens to be pi squared divided by log n plus 3 log n squared. So making this choice, then everything that I said in the prediction is true. So then for all k greater or equal than 1, and for all t strictly positive, then the ancestral partition process speeding up time by log n cube converge to the Boltzmann coefficient. I think this is the right constant. I think it's the right constant. I'm looking at. Okay, so that's the result. One additional feature of this that I want to point out is the fact that you have to make the wall move at this exact velocity. Okay, root of 2 minus pi squared over log n plus 3 log n squared is exactly related to the prediction that Brownian and Derrida made, that actually in this fixed size population, the limiting velocity of the cloud is approximately root 2 minus a constant over log n squared. So this matches perfectly with their prediction from that point of view as well. Okay, so are there any questions about this?
The size of the population is now only randomly constant.
Yeah, that's right. It's of order n,
So
but n times a random variable.
So now you can pinpoint the speed precisely compared to them because they kept the
Yes.
size precisely and they only had sort of their asymptotic similarity.
Yes, exactly. So it was. I mean, there's in fact not much reason that these two systems have to be exactly the same, but they turn out to do behave the same. I mean, that's actually the case, but it's not obvious to me why they should really behave. So in fact, one of the I mean, that's something that I still don't understand, why this fixed size population and this moving wall models behave similarly. I really don't understand really in the end why they're the same. I mean, I can vaguely wave my hands, but at a precise level, I don't really understand that. One of the features of the model that we consider, and the reason it's much, much easier to understand and to analyze, is that the fact that we've replaced selection by this moving wall means that particles behave independently of one another. They don't care about other particles, they just care about themselves. Whereas in the fixed size population model, you see that it's very important to keep track of the entire cloud of particles in order to say something about it, how it's going to evolve. Here, I can only keep track of myself. Okay, so there's much more independence in the end. That's why we can do things in this model. I, of course, don't have much time for proof, especially since the paper is quite long.
It's
Yeah.
really a bit of a miracle that you found a process which is essentially independent, modeling very precisely a highly
Yeah.
independent one.
Yeah. Yes.
So essentially, their considerations suggest that the cloud should move with this speed, and then if you assume that speed, you can prove that it converges.
Well, we can't actually deduce that, but that was the hope when we set up this model. Okay, I mean it's made to capture this effect, and it does capture it, which is kind of a miracle. I mean, it's a forced miracle, of course. But, so I want to say very briefly what is the reason. I mean, you see that one particular feature of this model also that I think is very interesting is that in the end, this coalescent process completely lose track of space. So there's no, you don't take into account where actually are these particles. The coalescent process is something that's completely homogeneous in time, and it's its own, it's Markovian with respect to its own information. So you don't need to know anything more than than how many lineages are there at any given time. I don't care to know where they are in the population. So this is one of the things that's very surprising, I think, about this conclusion. And so maybe what I'll do is I'll very, very briefly, in 5 minutes, explain where this loss of space, this loss of spatial structure comes from. And in fact, once you have made this calculation, a lot of things become simpler. So very basic sketch of proof, very basic idea. The very basic idea is the following. So first, so what we do really in this proof, what we do is we really try to prove this prediction that actually once in a while, every log n cubed units of time, you have a particle that makes it 3 log n away from the rest of the population. Okay, and then we separately try to handle what happens once you have a particle there, and why does it generate a positive fraction of the population? Why are the rates exactly what you need to get the Boltzmann-Schneemann coalescent? So first, we define this special level L to be okay. So one thing that I should before I do that, one thing that I should say is rather than having the wall move and killing particle when they hit the wall, one thing that I can do is just subtract. Okay, so I can see everything in the referential of the wall, and in effect, this is giving a drift negative mu to every particle, and I kill particles when they hit 0. Okay, so kill particles when hit 0, and drift minus mu to every particle. So I want to define this special position where particles, once they hit it, they're in good position. So define L to be exactly what I'm looking for, which is 1 over root 2 log n plus 3 log n. Okay, that's what I want to do. And initially, what I'm going to look at is I'm going to consider a single Brownian motion with no drift and kill both at 0 and L. Okay, eventually what I want to do is describe the system where particles are killed both at 0 and L, because I think L is a very special position, and I want to know how often do particles reach that position. So if I have one single Brownian motion at killed at 0 and L, I can look at the transition function, transition probability. So that's, if you start a particle at x between 0 and L, you kill it if it reaches 0 and L, 0 L. What's the probability that at time t it's still alive and it's in position y? So it turned out that this we can express very explicitly, because essentially this solves the heat equation with 0 boundary condition 0 and L. So there's an expression for this, which is which just involves summing over eigenfunction of the Laplacian with 0, Dirichlet Laplacian. So it's not very difficult to do that. So the eigenvalue are n squared, pi squared t over 2n squared, and then you have the eigenfunction, which are just sine n pi x over L. Okay, so if you add branching at rate 1, and if you add a drift, add branching at rate 1 and drift minus mu, so I can look at qtxy, and this is start with one particle at x. What is the expected number of particles in position y after time t that are still alive? Okay, so it's not very difficult to see what happens. You have e to the t times ptxy. So this basically accounts for branching at time t. If I let a free system of particles branch at rate 1, then I have e to the t particles. And this is a transition density for one Brownian motion killed at 0 and L, but there's no drift. So in order to account for the drift, I use what's this wonderful Gersonov theorem. Okay, so this is branching, and this is drift. So this is Gersonov theorem. Okay, so you see that when t becomes large, I have this infinite sum, but what I can do is I can ignore everything but the first term in this sum, because the exponents become exponentially smaller. Okay, so when I do that, and so you see that for this to be true, I have to assume that t is much larger than L squared, which on our time scale is very small. So essentially, instantaneously, we have that qt of xy. So we have e to the t, and then what's the first term? It's so there's 2 over L, e to the minus pi squared t over 2L squared, and sine pi x over L, sine pi y over L, and then we have this Gersonov term. And this term, I'm going to write it like that: e to the mu x, e to the minus mu y, e to the minus mu square t over 2. So I can rearrange this expression a bit. So we have exponential of t to the 1 minus pi square t over 2L squared, and minus mu square over 2. And then there's the e to the mu x sine pi x over L, and then there's e to the minus mu y sine pi y over L. Oops, there's no t here. So you see that one thing that would be great would be if this term here would be equal to 0. Okay, and it just so happens that with my choice of mu and L, this is equal to 0. Okay, so I have an expression which is independent of time. So this is telling me that actually after time t, when t is large, there is a certain density of particles which is stationary in time, which means that particles settle to some sort of equilibrium configuration after some time of order L squared. In effect, this is the beginning of the reason why we start losing the notion of spatial structure in this model. It's because whatever you do in this system, very quickly, the particle that you generate, they settle into the same equilibrium distribution. Note also that this equilibrium distribution is given by this function here, e to the minus mu y sine pi y over L. It's not dependent on x itself. Okay, it's proportional. So if I have a particle in x, it leaves a certain profile of particles with density proportional to that, independent of x, and the intensity is proportional to this as a function of the starting point. Okay, and this is the key thing. So it doesn't matter where particles are; they all give rise to the same profile of density a bit later of time, and this density is the same, and the intensity depends on their respective position. So you see that the more x is to the right, and the more I leave particles. So this suggests. So I'm not going to say much more than that. I'm just going to say that this suggests looking at the following process, z of t is going to be the sum over all particles of this quantity here. E to the mu times their position times sine pi of the position divided by L. And what this calculation tells us is that everything that I care about in this process is proportional to z. If I want to look at the population size just a tiny bit later, it will be proportional to z of t. Okay? If I compute z at a given time, then eventually, just a tiny bit later, L squared units of time later, then the population size will be proportional to z with a certain constant factor that I can tell you what it is. Okay? So if I have two configurations of particles and they have the same z, then eventually, very quickly after, they have the same population size. Okay, so it's true for the population size, and it's true for essentially every quantity that you could care for. Things like the rate at which particles hit L, for instance, because of this calculation, is also proportional to z. So in the end, this becomes the only quantity that I have to keep track of. And it becomes easy to do analysis on this one quantity that describes entirely the system. And in particular, it's a martingale because of this cancellation. So lots of things become easier to do. And I guess I'll stop here because I'm already over time. So thanks.
Thanks very much. Are there any questions? I found it terribly interesting, though. I mean, this looks like I'm overstretching the word probably, but this is another miracle. Essentially, you found one quantity which is a sort of Fourier coefficient, if you want to see, which is actually summing up the evolution of something highly complicated.
Yeah, that's exactly it.
So, yeah. So
and we'd like to do the same thing for the fixed size population, and more seriously, a bit answering the question that you raised earlier, to try to see what this is telling us about more realistic systems of evolution. Because, as you said, this sort of moving order is a bit strong, I think. Yeah.
But could it be that some way? I mean, you can think as a PE person, you start to expand your stuff in Fourier series. You know, like you have now sort of a basic process to try to mix it to the other extreme or whatever to get sort of more effects in, and you keep it sort of on a finite dimensional level in terms of Fourier coefficients of something which you might be able, I mean, to sort of approximate something which is more realistic or something.
Right. I mean, that's certainly is one of the hopes. And maybe when you have a more constrained system, maybe you would have to keep track of more things than just one. But I really just don't know at this stage how to proceed. I should say that there's another point of view to this whole, to this whole set of problems, which is closer to PDEs, because in some way you can try to think of this cloud of particles. You can try to describe them. You can think of the distribution, if you want, of these particles. And the original arguments of Brownian and Derrida are PDE arguments. They involve thinking of this cloud of particles as essentially a solution to a certain stochastic PDE. It's basically the KPP equation, so traveling wave equation perturbed by some Wright-Fisher noise. Why is Wright-Fisher should be clear. I mean, it's population model, and then thinking about it in these terms. So that's another direction that I didn't pursue because I'm not an expert in PDEs, but some people in my family are. So.
that there's going to be a beep, 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 beep.
Well, we're hoping for it.
How about other questions?
Why were the two physicists interested in this model to begin with?
Sorry, why?
Why were the physicists interested in this model to begin with?
Oh, yeah. Yeah, that's a very good question, actually. In fact, it turned out that the Boltzmann-Schneemann coalescent is the universal scaling limit for some models appearing in spin glass. And I mean, I could go on and tell you exactly how this works, but it's actually not a coincidence that the same object appears in both worlds. In fact, there is a way of thinking of this model as a spin glass model. It's one of the nice things I think about this particular set of questions, that you can think of it both in biological terms and in physical terms. And that certainly helps formulating some of the conjectures. That's one of the motivating, that's really one of the motivating ideas behind this. This is also related to the story of traveling equations perturbed by noise. So Brownian and Derrida had made lots of predictions about the speed of propagating fronts in traveling equations, in reaction diffusion equations, when there is some noise added to it. This is also related to the spin glass story, and all this fits together very nicely. But the big picture is absolutely missing. I mean, we're really very far from putting all these pieces together.
More questions?
But then eventually this approach to include selection into the Kingman coalescent, or to extend the Kingman coalescent, might still be much more tractable than the ancestral selection process introduced by Krohn and Neuhauser, isn't it?
That's something I have to say. I haven't thought very much about this direction at all. How does it fit? I mean, you had a question similar. How does it fit with the body of work, which is a large body of work on that classical models of selection? I haven't thought very much of this. That's because I've been very busy finishing this. It's already appeared now, by the way, but well, it's on the archive at least. But so I don't know for the moment how to do any of this for any more classical model of selection.
But that classical model of using selection in the coalescence theory, right? So,
Yeah.
so it would make sense to be able to relate it.
But this
So
model is so
normally-
different.
Normally, you run the selection as deterministic, then you condition back, right? Something like that.
Okay. So you mean sort of you do the usual Moran model, but you have two allelic types, and one type is stronger than the other.
Yeah, that's what Krohn and Neuhauser
Yeah, okay.
actually did. But then you get something much more complicated than the Kingman coalescent,
Yes.
because some individuals have a
Right.
inherently higher probability to produce offspring, and that's
But so I see. I mean, at least if that's what I'm thinking about, I see a big difference between these sort of models and the one that I was just talking about, which is the fact that, talking of just two types is really not at all the same thing as this sort of things, because here we have really every individual is its own type. I mean, the fitness is changing all the time. That means
the interaction
Yeah.
eventually.
Yeah.
And in the classical model, you have even more. You have much more interaction.
right. Yeah, exactly. So that's but that's something that I'm thinking about at the moment. Is really how does it fit in with other models of selection. One of the things that I'd be very keen to see would be, is there a natural way to interpolate between these models with selection and these models without selection? So there's a whole world of lambda coalescence that you alluded to, and there are some very natural candidates of lambda coalescence that do interpolate between Kingman's coalescence and Boltzmann-Schneemann coalescence. The question is, which model do they come from? And this we don't know. So we know the answer, but not the question.
Inverse problem. There was another question.
Yes, I was wondering about this log n cube, whether you can give some intuition or some idea why this is claimed that this is the wide scaling limit.
No, it's not trivial at all. I mean, I can give you some ideas of where exactly the scaling log n cube comes from. But in the end, what I can explain is from a calculation.
Oh, okay.
And you know, I don't think there's you know an intuitive explanation that says, oh yeah, of course, it must be that. That's one of the big surprises, I think, of their predictions, you know, the strange log and cube factor. One of the interesting things that seems to be true now, I mean, this has resurrected a lot of interest in branching random walks in the probability community. And it seems that this cube exponent actually shows up absolutely everywhere now. So there's a lot of problems where this cubic exponent shows up, and it's quite interesting. This has branching random walk, branching random motion is a very classical topic. And it's around at least for 30 years, 4 years maybe. And this is something that wasn't really discussed before.
Well, if there are no more questions, maybe we should thank Nathaniel again, as well as all of the other speakers.